Continuing our talk with plant interactions and limitations. Previously we looked at gradients within site limitations, and common themes that come up are soil, climate, disturbance, which is always a major factor in the way forests are shaped and changed, and of course time. These are all on the macro scale, on the large scale. Okay, but the following gradients are considered on the micro scale. Based upon factors found at the site level. So, top down, we're looking at macro scale, the big picture, but within the forest itself, on the smaller scale, on the individual tree, there are things going on. So, we're going to look at some of the limitations, what is limiting certain species from growing on a given site. And that's what this list that we're about to compile here is going to be. So, in this one, photosynthesis and respiration. Okay, every plant obviously needs to produce photosynthesis. Okay, and by producing photosynthesis, they are building energy and essentially food, if you will, and by doing that they are able to complete the process of respiration, which essentially means they are living and growing and using the energy that has been created by photosynthesis. On some sites, though, the intensity of sunlight can have a major influence, though, on growth and on respiration. So photosynthesis is increased by light intensity. Okay, the brighter the light, the brighter the sunshine, the greater the intensity of that light for the plant. Shade-tolerant species, if you look at your Silvix notes, you'll notice the species that are more shade-tolerant. They are able to photosynthesize at a lower light intensity and still maintain life. Okay, and so the compensation point is that level in which a plant can produce enough photosynthesis to survive. Okay, so down in this example, we have some sugar maple, and you'll notice that there is some speckles of light coming through, just little bits. Okay, so this forest site is only getting so much sunlight during the day, or good light intensity, because it's obviously shaded from the overstory. But our sugar maples, although they're in the shade, they are quite shade tolerant, so they're able to handle that type of growing situation. Okay, so in that case, maybe 0.3 to 1.5% full sunlight for individual leaves. Okay, but overall, the plant or the tree itself is able to survive in about 5% full sunlight. Okay, so that's more of a shade-tolerant species. That is an incredibly little amount of direct sunlight. Okay, and for the individual leaves themselves, 0.3 to 1.5%, that's not a lot of light, yet they're just able to survive. The other example, needing more like 30% full sunlight, and keep in mind the amount of darkness a day has throughout the nighttime. 30% sunlight is quite an intense amount of sunlight, and that is for the more shade intolerant species such as jack pine, where they really do require a lot of sunshine in order to survive. Other limitations: water. Okay, capillary water. How much water can be made available to trees? Because remember that soil will lock up a certain amount of water and be in a position that is unavailable for trees or for growth. Okay, so most growth occurs at a soil moisture tension less than 6 bars. Bars is a unit of measurement, and not to get too caught up in the different units of measurement, but what I'm just trying to say here is that a tree needs to exert more force to take this water than the tension within the soil. Okay, and so if it's gravitational water, that's water that's available to the tree, it's easily taken up. but capillary water is water that is more difficult or might be bound up and cannot be taken unless respiration or energy is used from the tree in order to draw it from the soil, less available water. Okay, so water is one limitation for trees. Also, we have nutrients or elements. Generally stored in the leaves, phloem, buds, root tips, reproductive organs, in other words, the living parts of the tree. Influenced by pH, mycorrhizal associations, and the benefits they provide. Okay, so nitrogen fixation, especially with some species such as plants within the legume family, they have a greater advantage to nitrogen fixation because of the mycorrhizal associations that they have with different associates within the soil. And then, of course, with pH, the influence that plays by acting as a block during certain pH levels for certain elements. Microorganisms obtain energy from plant and animal parts. Respiration takes place when decomposition is taking place. Okay, so in other words, when microorganisms are ingesting and decomposing plants, and when that takes place, they are respiring, if you will. And what that does is it releases carbon dioxide, water, heat, and inorganic matters. Okay, and so all of this is taking place in most cases down here on the forest floor. Okay, so they're breaking down this layer, and while they are doing that, the microorganisms, because they are respiring, they are producing carbon dioxide. Part of the decomposition process and the digestion of this microorganism, or of the decomposition, is a byproduct is water, heat, and inorganic nutrients as it decomposes, and those are the things that are helping create a microsite for growth of plants and also providing the elements in the water needed for growth. So therefore, it's in the best interest of trees to establish symbiotic relationships with mycorrhiza. And globally, on a forested setting, most plants benefit from the associations with mycorrhiza fungi. Okay, quick little case study here, but we've got two different forest types. The first one on the left being a rainforest, you'll see that it is lush, lots of growth, but very little forest litter. And on the right, there's an example of boreal forest in Canada. Lots of downwoody debris, fine dead foliage, and larger stumps and logs and things like that. So, what's the difference in these two forest types? Well, in the rainforest, the decomposition rate is so rapid, and the soils can, in many cases, be quite sandy, where there is a lot of leaching and a lot of rainwater, more so to leach away some of the elements. The trees are trying to grab up as much as they can, but the litter layer is turning over very quickly because of the climate and because of the soil and the moisture levels. Here, in the boreal example, you've got the long layover with winter, where that interrupts the decomposition cycle. So the litter ends up piling up here and doesn't decompose as quickly. So, in essence, on the boreal setting here, a lot of the elements can be tied up and not available to the tree because they have yet to be decomposed.